All right, good morning. Hi, everyone. Hope you all are having a good day so far. The plan today is to continue our discussion about magnetism and magnetic fields. Let's just go ahead and jump right into it. Share. Okay, great. So yesterday we ended with this, talking about this idea that moving charged particles generate a magnetic field. And we could understand that by this relationship that we see here, that the B field comes about if I have a charged particle with a velocity, okay, that's moving through space. And I can define this position vector, right, this displacement vector R that points from that moving charge out to some point in space where I want to probe to see what the magnetic field looks like at that point in space. Okay. We said we could find the direction of the magnetic field using our right-hand rule. We take our index finger and align it with the vector that would be Q times V. Take our middle finger, align it with the R hat vector, and our thumb will then point in the direction of B. Right, that's the right-hand rule is what the resulting vector you get generically when you use a cross product. And we saw that the fundamental units of the magnetic field are the Tesla, right? Those units are encoded in this physical constant mu naught. Okay. And the charge and velocity and distance metrics in this equation are all our standard sets. We're going to extend this idea today to talk about what happens if I have a collection of moving charged particles, and how can I construct with this understanding that I can generate magnetic fields from moving charges. How can I construct interesting magnetic fields that can be useful for, say, some specific applications? And the general idea is something we've seen for lots of different physical phenomenon, that if I have, say, two moving charged particles, say I have charged particle 1, and it's moving with velocity v, and I have a charged particle 2 over here in space, and it's moving with velocity v2. And I want to know, what does the magnetic field look like in this point at this region in space? Well, I could find the magnetic field coming from particle 1, right? I could define an R hat vector and use the Biot-Savart law that we see on the left-hand side here. And I could calculate a magnetic field coming from object 1. Similarly, I could define an R hat vector coming from Q2. I could calculate that, right? And I could find this angle theta between each of them, and I could calculate that cross product, and I could find the magnitude and direction of the B field. Okay. And so I could find B2. And each of those moving charged particles is contributing to the total magnetic field in space. So if we want to find the total magnetic field, we just are able to use our superposition principle that'll tell us that B total is equal to, say, B1 plus B2. Something like this. And notice it's a vector sum, so we have to pay attention to the directionality of the B fields, right? If one of them created a B field that points up and the other one created a B field that pointed down at that point in space, they would cancel each other out because of the vector nature of the magnetic fields. So that means that if I had, say, I had a wire then that was carrying some current I. Well, we know current I is just some amount of charge that's moving across some position at a given instance in time. Now what we could do is, right, so this is like a collection of a bunch of charge that's moving through this wire. And what we could imagine doing is breaking this current carrying wire up into small segments, ds, tiny, tiny little segments that each of them is going to carry some small amount of fundamental charge dq. And so we can think about current carrying wires like large ensembles of moving charged particles. And so if I want to know the magnetic field at this point in space, I could divide this magnet up into a bunch of little regions, find the charge in each of the little regions and sum up, right, integrate over that space, right? I could find the ds here, and I could do something like the total B at that space would be something like the integral of dq times the velocity. Well, the velocity is going to be encoded in the current there. The velocity is going to be something like my ds over dt, and you can see that, right? And then I'm going to have, you know, physical constants r squared mu naught over 4 pi, etc. Well, you can see that I get some interesting things coming out. I get a dq dt that's something like the current through that little area. And so this starts to look like I get something that's like a little, that looks like the current times some differential r squared. And I can integrate this over, right, all the positions in this, across this wire, and do the vector summation to find the total magnetic field at this position. Your book walks through this in detail, but the important thing is the result of that calculation. Why can I not change slides here? Hello. Okay. The important thing is that with that simple technique using superposition principle and breaking up complicated moving charge distributions into small individual pieces that I can apply my fundamental law, I can find interesting relationships for collections of moving charges that are set up in a specific way. For instance, we can find that if I have a straight wire, that it generates a magnetic field that circulates around it, and it has a strength that's proportional to the current that's flowing through the wire and falls off like 1 over the distance as I move further away from the wire. If I have a current carrying loop, right, so we're looking at a cross section here where I have current flowing into this loop on the top, flowing out of the loop back towards me, coming towards me at the top, flowing back into the loop on the bottom. What this ends up generating is a magnetic field that looks like a sort of like a permanent magnet, where I have most of the flux, most of the magnetic field in the center, oriented in this direction, perpendicular to the plane defined by the ring, where I have a north side over here and I have a south side on this side. Okay. And you can imagine that if you use, right, if you think about each of these little bits like a moving, like current, and you can use your right-hand rule to see that the magnetic field coming from this current coming out of the board points in this direction. The magnetic field coming from this current flowing into the board on the bottom also points in the same direction inside of the loop. And so they add together to give me that, you know, that field that points in this, you know, that points as I have indicated here. And outside of the loop, right, the magnetic field coming from this upper part would point in this direction. The magnetic field coming from the lower point would point in the opposite direction, and I would get some cancellation of the field. And it leaves me with something that looks just like the magnetic field that comes from a permanent magnet, where I have a strong north side and south side, and then very little magnetic field on the edges. The magnitude of that thing we can relate to the amount of current that's flowing in the wire and the radius of that loop, okay. And how many different turns we have. Okay. And so once we've established that we can generate magnetic field with these individual rings, we can imagine just putting stacks of those rings together in some sort of a thing that we call a solenoid. So they're not individual rings, but it's just a coiled up piece of wire. So I'm essentially taking loop after loop after loop of this current carrier. And I can find that, again, it creates a magnetic field that points in one direction through the center of the loop with basically no magnetic field outside of it. And it has a strength that's proportional to the current, the number of turns, and the length of this solenoid here.
Professor.
Yes, sir.
So back on the loop,
Yeah.
uh, is the radius from like the middle of the ring, or is it from one of the edges?
Is
Like,
the, yeah.
like the thickness of the ring. Like, does the thickness of the ring matter?
Oh, you mean like the thickness of the wire? Is that what you're asking about? So
Yeah. So I'm
they're talking about, so that radius is the radius from, let me draw it. It's the radius from the center of the loop.
okay. So it's from the center of the loop to the center of the wire in
To the
the.
center of the wire. Yeah, I mean, here we're thinking about the wire. This is an approximation where the wire is very small compared to the radius of the loop. So essentially, the radius of the wire isn't coming into play here. You can just think about it all at one point at the edge of the loop.
Okay. Thank you.
Yep. Okay, there's one other law that your book introduces. It's one of the fundamental relationships between charges and fields. It's called Ampere's law. And your book goes through a bit of a derivation. And this thing here is what's called a path integral. Okay, and what does this law says? So one thing is these path integrals can be pretty tricky to set up, except in very special circumstances. And so we're not going to have a huge focus on setting up these formal calculations for Ampere's law. But we do want to understand in general the principle that it's pointing to, right? What does this say? This says that if I have some current, so here's say a loop. Sorry, let me erase this. If I have some current, so say here's a wire with current flowing into my page. If I pick some loop, some path around this current, okay, we know that that current is going to generate some magnetic field. The magnetic field is going to be circulating around the current. What direction is it going to circulate? Well, I can use my right-hand rule. I'm going to point my thumb in the direction of the current. My fingers circulate around like the magnetic field. So the magnetic field would circulate around this current, something like this. So I have this B field everywhere around this. And if I were to pick, right, if I were to pick this all to be at a constant R, if I imagined that I had centered that current around this loop that I tried to draw here, well, then I could calculate this path integral. All this path integral is saying is take the component, so this is B dot ds. So ds is going to be some little segment that points along my path that takes me around this path. So there's a bunch of little ds's and they're turning around and they're moving with the path that I've chosen here. If I move around that path, this dot product, if I do B dot ds, it means pick out the component of the B field that's perpendicular, or sorry, that's tangential to the path, right? Remember, a dot product gives me something that's like B ds sine of theta. It's going to pick out the component that points tangential to the circle. So if I have a component of B field that's perpendicular to my path, it won't contribute to this path integral. If I have a component of the B field that points along my path, it will contribute to this path integral. And then I just integrate that up as I go around this loop. Well, if B field is constant, say if I pick a constant radius here, then this is a special case. If that B field is constant, I can pull it outside of this, right? And this would just be the perpendicular component, or sorry, the parallel component of the B field. And then this integral ds is just going to be the total path length, how far I have to walk around that path. And the interesting relationship you find is that that quantity equals mu naught times whatever current is passing through your closed loop. This is very analogous to Gauss's law. Remember, Gauss's law told us that the electric flux through a closed surface is just proportional to the enclosed charge inside of that loop. So when saying a similar thing, it's saying that if I find some B field, some total value for the B field as I walk around a closed path, right, for this path integral, it implies that there's some non-zero current contained inside of that path. we can right? I mean, proving that is a pretty complicated endeavor, but imagine, right, we can get the idea. You can see that for this closed loop with the current inside of it, you can see the B field circulates around and always points in the direction of my ds. So it's going to continually add a positive contribution to that integral and give me a non-zero value for my path integral. If I were to pick a loop that's, say, outside of the current, right? Well, what does the B field look like? Well, the B field everywhere on this side, right? Let's see, how is the B field going to point? Well, over here, it's going to point down. Over here, it's going to be weaker and point down. Up here, the B field is going to be pointing something like this. Right, remember, the B field wants to be circulating around. What does it do here? It wants to be pointing something like this. Okay. The B field is going to be, wants to circulate around that charge. So you can imagine now as I move around this path, if I pick these little DS's, well, over here, right in this region, the B field and my little path vectors are going to have components that are aligned. But as I come around this side here, now you can see that my ds and my field vectors are going to have components that are anti-aligned, that are going to give me a negative product for the dot. They're going to give me a negative product for the dot, for that dot product in Ampere's law. And the net effect is that as I go around that loop, that path integral, the positive contribution will completely cancel out with that negative contribution, and I'll end up with zero value for that path integral. Okay. So if I find non-zero magnetic field summed up around some, right, non-zero contribution to this path integral as I go around a closed loop, I know then that I have some charge enclosed in that loop. All right, so let's play around and see if we can answer some questions about field coming from some interesting charge distribution using these relationships here. So here's a current carrying wire. Okay, the current's pointing in this direction, up, flowing. You imagine the wire just extends off to infinity off the top of the page here. How does the magnetic field compare at points A and B? Let's see if we can do that one. Let me do the polling. I'm gonna give you guys 5 more seconds. Okay, let's go ahead and end the poll. All right, so many of you selected B, that it's half as strong but in the opposite direction, and but there were split answers kind of across the board here. All right, well, let's see. What's the answer? What's the functional form? What's the functional form for that current? Well, we just saw on the previous page that for a current carrying wire, the B field has a magnitude that's equal to mu naught times the current over R. And there's a factor of 2 pi, I think, somewhere in there. Something like this. And we have to use the right-hand rule to determine the directionality. Okay, so let's start with the directions. So at A, what direction does the magnetic field point at A? Well, I'm going to use my right-hand rule. My right-hand rule when I'm dealing with current flowing through a wire tells me I'm going to align my thumb with that current that's pointing upwards using my right hand, and my fingers are going to circulate around that current in the direction of the magnetic field. So at this point, the magnetic field has to be coming out towards me. And if I use that same thing, my fingers are pointing up over at B, for that magnetic field to be circulating around the current, the field has to point into the board here, into the page. Okay. So the fields point in opposite directions at A and B. Okay, so I can eliminate these answers that say same direction. What about the magnetic field? Well, it falls off like one over the distance here. So if this is B field 1, I'm twice as far when I get to away from that current carrying wire. So this has to have a strength B2 that's going to be half of B1. For the infinite current carry wire, the thing falls off like 1 over R. That's again because I'm integrating the strength, right? Remember, for a single point particle generating magnetic field, it falls off like 1 over R squared. But now I have this long train of moving charged particles, and so it falls off less quickly because they're all contributing some piece of magnetic field at that position B. Half as strong, opposite direction. What about this one? Let's just focus on the direction. So now I've got a current carrying wire. Okay, so there's current flowing around this thing in the direction indicated by these arrows. If I look at point P, what direction does the magnetic field point at that point in space? Okay, I'm going to end the poll. So we had some split results between into the screen and out of the screen. Well, let's divide this up. Let's focus on what the magnetic field looks like from the current that's flowing in this top branch versus this current that's flowing in the lower branch. Notice that, right? Notice here that the current flowing through the upper branch of that wire is going in the opposite direction, right? Loops around in the opposite direction as the current flowing in this red path that I drew here. So let's call this lower, and let's call this one upper. What direction is the magnetic field coming from the lower wire? Well, let's see, I can use my right-hand rule. If I just look at the current flowing at any point, I can point my thumb in the direction of the current flowing around that lower loop and curl my fingers around that wire and find that the magnetic field coming from that lower loop wants to point into the page here. I can play the same game for that upper loop, right? I'm going to point my thumb in the direction of the current around that upper loop. My fingers are going to curl in the direction that the magnetic field should point, and so I'm going to get a magnetic field that wants to come out of the page at me. So at that point in space, I get a contribution from those two loops. They point in opposite directions. Which one has the larger magnitude? Which one has the larger magnitude? Well, the field falls off with respect to the distance, right? You could think about this either like a current carrying wire or like half of the loop. Either way, we see that it falls off something like 1 over the distance that I am away from the current. And so since I'm further away from this upper loop that carries the same current as the lower loop, the magnitude, right, B lower has to be greater than B upper. And I'm going to end up with some net magnetic field that points into the page. Okay. So I have the magnetic field coming from that upper branch and lower branch point in opposite directions, but because P is closer to that lower branch, that has the stronger magnetic field due to proximity, and so the the magnetic field from that upper branch can't completely cancel out the field coming from the lower branch. Okay, what about this one? Let's look at a current carrying loop. So here I have a cross section of a current carrying loop. There's current flowing into the loop on the left-hand side here, coming out of the loop on the right-hand side. What direction does the magnetic field point through this loop? So the magnetic field points in the direction of what we call the North Pole. Where's the North Pole for this current carrying loop? I'm gonna give you guys about 5 more seconds. Okay, let's go ahead and end. Okay, so a lot of you said the north is on the bottom side. Let's check that. Let's first look at the magnetic field coming from these individual pieces. What direction does the magnetic field come from this current that's flowing into the page over here, say at the center of the loop? Well, if I do that, I can point my thumb in the direction that into the page, and over there at the center of the loop, then my fingers curl around and point downwards. So the B field here points down. Oops. What about for the other branch here? Well, now the magnetic field comes out, so I point my finger coming out of the page, I loop my finger around that current, and again, I find in the center that the magnetic field points down. Okay, those two would sum together to give me something, right? Like the total magnetic field. So the magnetic field points down here. Another way to do this that works with the right-hand rule for loops is to take your fingers that are not your thumb and to wrap them around the loop in the direction of the current, and then your thumb will point in the direction of the B field through the center of the loop. So if I point, I can see that the current flows in on the left, wraps around to the right, so I get that the B field has to point downwards here. Once I see the direction of the B field, then just by convention, we label the direction of the B field pointing towards the north side of our magnetic setup here. What if I did this? What if I have a current carrying loop and I find that the magnetic field, right? I have a magnet that I know where the north and south are. I have those labeled on that magnet. And I bring the south end near this loop. And what I find is that there's a repulsive force. I feel that magnet pushed away. Can you tell me how the current is flowing around in this loop? What direction is the current flowing around in the loop? Okay, let's go ahead and stop here. Most popular answer was B, that it goes in at the top and out at the bottom. Well, let's see here. If I'm feeling a repulsive force, right, these two objects are pushing each other apart. That means that for this loop, I should have a south side on this side of the loop and a north side of my magnet on this side of the loop, because we want those like poles. We know that's going to repel each other, right? It's just like if I brought two permanent magnets together, I want the two like poles pointing together to get this repulsive force. If I want that to be the north side and this to be the south side, it means I know that I want the magnetic field through that loop to point to the left in this example. Well, what direction does my current need to flow to generate a magnetic field that points to the left? Well, I can use my right-hand rule. I can align my thumb with the magnetic field, and my fingers then are going to curl in the direction that the current has to be flowing around in that loop. That means the current has to flow in at the top and out at the bottom. What about this one? Can we do a simple analysis of the field integral around this using Ampere's law? So let's remind ourselves what Ampere's law said. It said if I do this path integral of B dotted into ds, that this is just equal to mu naught times the enclosed charge, or sorry, the enclosed current. Can you calculate the line integral of B around the loop? Or sorry, I'm reading the problem wrong. We know what that integral is. They give it to us, that it's mu naught times 7 amps. Can you determine what I3 has to be in this example? What's that unknown current there? Okay, let me go ahead and end the poll. Share the results. Most of you selected C, that it has to be 1 amp into the screen. That's right, right? In order to get, right, so first of all, in this bit, we want the I enclosed. That's gonna be like mu naught. I1 isn't enclosed, so we don't care about that one. It's not contained inside of the loop. So this is gonna be mu naught I2 plus I3. We can see from up here that that sum has to be 7 amps. If I2 is equal to 8 amps, then that means I3 has to be a negative 1 amp. Okay. So that means it has to be 1 amp pointing in the opposite direction of I2, so it has to be 1 amp into the screen. Okay, what about this one? What's the value of this path integral going to be? All right, let's go ahead and end the poll. Share the results. Most of you selected B. Okay. Well, we know that this thing is like mu naught times the enclosed charge. What about the sign of this thing though, right? There are two answers. So it can't be this, it's not gonna be the sum of those two guys because we see I1 and I2 point in opposite directions. Okay, so, and in principle, there's nothing telling us that they're the same current. So there's no necessity for this to be 0. If I1 was equal to I2, then this would be 0, but we don't know that a priori. So we're gonna come up with a more general expression here. How do we know which of the currents we want to assign the negative sign to? Does anybody have an idea?
Its magnetic field is in the opposite direction of the loop.
Yeah, so look, the loop has a directionality. Let's look at I1. I1, I can use my right-hand rule. So look, the current, or sorry, the B field coming from I1 is circulating in the same direction as the loop that I have drawn there, the path that I'm going to take around that charge. Okay. So that means when I do the dot product, because B and DS are going to be aligned, right, my DS's are going to point in this direction. I'm going to get a positive value for that path integral as I go around the loop from I1. Whereas if I do it for I2, because it's pointing down, the current or the magnetic field is going to be circulating against my path, and it's going to give me, that dot product is going to give me a negative value. So the contribution to the path integral from I2 is going to be negative, and from I1 is going to be positive. Okay, what about this? What about a solenoid? We saw that I can calculate the magnetic field from a solenoid. It was something like mu naught times the number of turns times the current flowing through the solenoid divided by the length of the solenoid. So I have two solenoids, 1 and 2, and I put the same current through each of them. Okay, you can see I have I flowing in this direction on both of these solenoids here. They're designed a little bit different. So the lower one has twice the diameter, twice the length, and twice as many turns as solenoid 1. Okay. So how does the field B2 at the center of the solenoid, at the center of solenoid 2 compared to B1 at the center of solenoid 1? Let's see what you guys think. Okay, let's go ahead and end the poll. So the most popular answer was C, that the magnetic fields are the same. Okay. Well, notice in this equation that, right, first of all, there's no dependence on the diameter, okay? So the fact that they have different diameters is inconsequential to the magnetic field here for this solenoid setup. We're not interested in the diameter. There is a length term, and there is a term that depends on the number of turns in that total distance, right? When we talk about L for these solenoids, we're talking about this total distance that the winding covers. So we could rewrite this thing. This is like mu naught NL times I. So the things that drive the strength of the magnetic field in the solenoid are the current. The more current you pump through it, the larger the magnetic field gets, but then also the number of turns per length. Okay. So that means if I double the length and at the same time I double the number of turns, that this ratio won't change and I'll end up with the same magnetic field. Well, that's exactly what I did here. I have twice the length, but twice as many turns. So that means that this number of loops per distance doesn't change, and I have the exact same magnetic field generated by each of them with that same current flowing in it. What about this one? Here's another solenoid, and I've identified, say with some external probe, the direction of the magnetic field through this thing. So this is the north side, this is the south side generated by this solenoid. What direction is the current flowing through this winding? Is it entering on the left-hand side? Is the current flowing in this direction? Or is the current flowing in this, coming in this side of the wire? Or would either of them produce the same field? What do you think? Where does the current enter this solenoid? Okay. We've got split answers here, okay? So even split between A and B here. So let's think about what's gonna happen. Let's just take a guess at this and see if we get, and see either we'll get the correct answer or the wrong one, and then it's probably the opposite guy. So let's just see what happens if I bring current in this way, right? So if I have current flowing in this direction, it's gonna loop around, and for right on this side, right, I'm gonna see the current would be going up for all these regions that I see in this diagram. Well, what direction would the magnetic field in the center of the loop be pointing? Let's just take a single loop. Just imagine one of those loops, okay? If I point my finger in the direction of that current, okay, and then I wrap my fingers around that current, well, the loop, then the current through that single loop, or sorry, the magnetic field through that single loop is gonna point in this direction. And each one of those loops is going to have magnetic field that points in the same direction, and it'll all sum together to give me that total magnetic field, but they'll all point in this direction. Okay, that's not the direction that's indicated by, right, the initial conditions of this thing. So let's try it the other way. Let's just convince ourselves that it worked. Let's get rid of that. And let's imagine that the current flows in this direction. So for that any one of these loops, that outer part of the loop that's closest to us, the current would be flowing down. Well, now I can point my finger down with that current, and I can see through the center of the loop that the magnetic field would be flowing in this direction, which is aligned with what I observed there. Again, you can also do this by taking your right hand, wrapping your fingers in the direction of the current, and your thumb, that the current is wrapping around, and your thumb will point in the direction of the magnetic field. So you can see if current comes in on the right-hand side, then the current is gonna curl around that loop, right? First it goes behind the coil, and then it comes around to the front, and so I get a magnetic field that points to the right. So this current has to enter on the right and exit on the left. Okay. So before we end today, I want to introduce the next concept that we're going to discuss related to magnetic fields. And that's that once so we've talked about how we can generate magnetic fields, right? I can generate magnetic fields from moving charged particles, and I can make interesting configurations of moving charged particles to sort of shape magnetic fields in ways that I would like for some specific application. Well, what do magnetic fields do once I generate it? Well, if you boil it down, the thing that they can do is they can apply a force to a moving charged particle. So if I already have, and here's the rule, the magnetic force that gets exerted on a moving charged particle is equal to QV cross B. Okay, notice it's another cross product relationship. So we can use the right-hand rule to understand the direction of the force. So here's a diagram. A positive particle here is moving to the right, and I've got magnetic field that's indicated by these blue X's. So I have magnetic field that's pointing into the board. Because I have a moving charged particle, then I can go ahead and I can calculate the direction of the force. I can align my index finger with QV. So what direction does QV point? QV points in this direction, same as the velocity because it's a positively charged particle. I can point my middle finger in the direction of B, the second vector in the cross product. So what do I do? V cross B, and then my thumb points upwards in the direction of the applied force. Okay. So particles, charged particles moving in a magnetic field experience a force. And the force, you can determine the direction of the force using the cross product between QV and the direction of the magnetic field. The magnitude of that force, right, is going to be something like QVB times the cosine of the angle between Q and B, or sorry, between V and B. Okay. This is the angle between QV and B. Well, we can extend this idea. We just said that a wire is a collection of moving charged particles. So if I put a wire with some current into a magnetic field, each of those charged particles is going to experience the force shown above here. And so I could integrate that force over the entire length of the wire, and there will be some net force pushing on the wire. Turns out you can calculate that, right? You can use an integral expression. You can break that wire up into a bunch of little charged pieces that are moving along the wire, and you find for this infinite wire that the force is equal to the current times L that points in the direction of the current, right? It depends on the length, right? What is L? L is the length in the field B. Right, so imagine the field B only lived in this one particular region and then the field turned off. That wire would experience a force due to that portion of the wire that's sat in that magnetic field. And then again, it's crossed with the magnetic field B. So I can use my cross product. I point my index finger, that's the first vector of the cross product, in the direction of the current. For that example on the right, I point my middle finger into the page in the direction of the indicated B field, and I get a force that pushes on the wire in the opposite direction here. That means also if I have a current carrying loop, okay, we know that that current carrying loop, if a current circulating around in this direction, wants to generate a magnetic field that has a north side that points in this direction from the right-hand rule. Okay. Well, if I put that in an external magnetic field that points in this direction, then that turns out what happens is that loop gains a torque that the north sides, right, these two north sides will be attracted to one another and the south sides will be repelled, and it wants to align that magnetic field with right, the two magnetic fields, the external magnetic field with the magnetic field being generated by the loop. And the torque applied is equal to something that's called the magnetic dipole moment, which we'll talk about more tomorrow, times the strength of the magnetic field. So let's just do this last problem and then we'll stop for today. And then tomorrow we'll just talk all about the forces that charged particles experience in magnetic fields. So if I have the field that's generated by that magnet shown in the slide here, and I have a charged particle moving as indicated here, what direction does the magnetic force point on this object? I'll give you guys, I know we're right at the end here, so I'll give you guys 15 seconds to answer. Okay. Remember, the force is equal to QV cross B. Okay, let's go ahead and end it. We're going to use our right-hand rule. We're going to align our index finger with QV, which points up. At that position, the B field, which is going to be my middle finger, points to the left. And so I end up with a force that points out of the screen towards me. So the bulk of you selected D out of the screen, and that's the correct answer. Okay, good. We're going to play more tomorrow with charged particles moving in magnetic fields and the forces that that are exerted on them, and that'll wrap up our discussion about this chapter. Okay, that's it for today. If you have any last questions, as usual, I'll stick around for a few seconds. And everybody have a great day, and I'll talk to you again tomorrow. All right, bye everyone.
Can you go to the slide where you had two coils, one of like a different length?
Yeah, give me 1 second. Let me pull the slides back up. This one?
Yes. So you said it was equal to each other.
Yeah.
I was looking at the videos, the video lectures,
Yeah.
and in that it says the coil center is equal to mu naught times Ni over R, where R is that radius and not the length.
Well, so there's two different things here, right? So
Oh, two different
there's
ones?
this there's the formula for the loop, right? A single loop, which is what I think you're pointing to here, right? That's mu naught over 2
Okay.
times the loop divided by R. Now the solenoid, all right, because I have multiple loops, you know, they all contribute, right? I think your book goes through the example, but you're essentially stacking up these different contributions, and it turns out that the radial part of this, that radial part of it drops out, and what you care about is that length, basically.
Okay.
Right, you can imagine that this thing, right, is somehow just depends on how many of those current carrying loops you can stack together, and it multiplies the more loops you can cram into like a fixed area. Okay, so there's two different formulas, right? There's one for the solenoid because you have multiple loops stacking together. That turns out that radial contribution vanishes. And then the solenoid depends on how many of those loops you can cram into a fixed area.
Is the solenoid the coil, or is that just multiple loops? Because his slide says for the coil, the number of turns in a coil. So I didn't know. I thought when you said solenoid, I just assumed that was the same thing.
Yeah, so the solenoid is a coil, right? So it's like one, so what you were thinking about here is this is like one, let's see. What we're thinking about here is that this solenoid, right, it's just a wire, right? A single wire that's just like wound around like this, right? It's just loops of wire like this. And the effect is, right, if you, and then you like, you can, the tightest you can make that is like if you push everything as close together, right? If you make the wires touch, essentially that's, imagine they were insulated wires, you could squeeze that coil down until they touched, and that's sort of as tight as you could pack it. And what you can think about is that each of these little coils, like as I go from, oh, let me pick a different color. As I go from here up to here, that essentially looks like a single current carrying loop. So it's like I have one loop, and then two loops, and then three loops, and then four loops, and then five loops here. And so the field is somehow the sum of the contribution coming from five, you know, independent loops in space there. Does that make sense?
Yeah. All right.
So a solenoid is just a coil of wire, but that coil of wire, you can approximate it by like a stack of current carrying loops.
Okay. Hold on 1 second. Oops.
Let me pull up, I'm pulling up on my computer real quick, the lecture slides that were probably in the video. Let me see what it says. Okay, well, Devin, I'm not finding this quick enough, but let me, I've got to open up the class to the session to the next class here momentarily. Let me get back at you on Slack after my next lecture, and I'll send you some clarification that hopefully will help you out.
Okay, thank you.
Okay, all right, have a good day. Thanks.
Thank you.